Thank you, John. And in fact, some of you probably were in my seminar last February. I think also end of January and February. And it's always a great pleasure to come to UC Santa Barbara. And last time I came, there was a snowstorm. I couldn't go back, so I had an extra day here. And this time, when I left, I left 10 days ago. I was barely able to leave Boston. So you see where the weather joyous. And it's a great pleasure, and I want to thank you. And today, I would like to talk about when I think about the 1 year, what additional topic, what additional thing I can bring in. And it's actually a challenge. I try to make it as distinct as possible from my last year's talk. So I'm going to share some of the work we're doing in the really in the photon area. Last time I focused on the phonon, the heat conduction. And our center is focused on the solar thermal. And so I'll start with this slide. If we think about currently how we are using solar energy, and of course photosynthesis and photovoltaics and solar heating and the solar thermal power plant. And in fact, one thing that probably is surprising to many people here is solar heating is widely used in China, and the deployment of the solar heating system is over 140 million square meters. And so that's this is a widely used. In a way, it's a high tech because it's actually a vacuum tube. It's an evacuated tube with selective surface coatings. So today, my talk is at the end, I'll talk about some solar steam generation that could have the application for both. I'll also talk a little bit on the photovoltaic. And but let me just use 2 slides to introduce the drivers for our center, the Energy Frontier Research Center, which is a solid-state solar thermal energy conversion center. And this center has 2 doors in terms of technology. One is thermoelectric, which a lot of people on this campus work on. Is basically using semiconductor, using temperature difference to drive the diffusion of charge from the hot to the cold side. And so what we're taking advantage is using the solar energy to create that temperature difference and generate electricity. So this was what I talked last year, and I'm not going to spend much time today on this, but we work a lot on also thermoelectric materials that are trying to engineer electron-phonon transport. But today's talk is more driven by the photovoltaic, and specifically in our center, we are exploring solar thermal photovoltaic. So the idea here is when we have solar radiation, it's a broadband. And we want to have an absorber to absorb the solar radiation and re-emit the radiation in a narrow band. And of course, if we know that if the energy of the photon is narrow band, then we can avoid a lot of loss of the excess energy above the band gap and also energy below the band gap. And it turns out that actually there's a theoretical study showing that those kind of solar thermal photovoltaic, in theory, you can achieve with one junction, you can achieve efficiency same as the infinite multi-junction cells. The challenge here is how we can engineer these absorbers and the emitters. And these absorbers and the emitters, selective absorber, where you want this absorber absorb the broadband solar radiation, but do not emit in the infrared range. And in the emitter, you want also only emit across the band gap. So we sort of transform the difficulty of doing the multi-junction cell into, say, the high temperature absorber and emitter using photonic crystals kind of structures. So that's the one of the motivation for our center, two technology drivers. And I will use this as a motivation for us to study radiation heat transfer, studying photovoltaics, and also steam generation. So I will cover three a little bit disparate topics today. The first one is more on the fundamental side, where we're looking into radiation heat transfer between two closely spaced surfaces. And in a way, the driver for us is when we absorb broadband solar radiation, the question is how we can deliver thermal radiation to the photovoltaic cell in a high power density, high flux. And one possible is the near field radiation. So let me start with the basic blackbody radiation law, which you all know. And the Planck's blackbody radiation law can be split into the energy per photon and the density of states in free space, the photon density of states, and then the Bose-Einstein distribution for the photon per states. And this is the energy density. And when we do the thermal radiation, we do the intensity, which is this energy propagating at the speed of light and propagating into all directions. So that's a solid angle of the space divided by 4 pi. And this will give you the intensity form for the Planck's law of blackbody. And if you integrate the overall spectrum of the the radiation from 0 to infinite frequency, you get the Stefan-Boltzmann law. So this is the standard in textbook, say blackbody radiation is the maximum of thermal emission. And the question is it really true? And if you go to read the textbook of Planck written in 1906, he was very careful, and he says throughout the following treatment, the dimension of all parts of space considered as well as radial curvature of all surface large compared to wavelengths of the ray considered. So he knows his theory is only valid in macro scale, not in the situation when the spacing is comparable to the wavelengths. So let me use a simple picture here to explain. So when we have two parallel plates, we're looking into thermal radiation between hot and cold. And of course, we know thermal radiation is the source is the either electronic transition or the lattice vibration. So it's the electromagnetic wave propagation. And when we have a medium, there is a critical angle of incidence. So only the rays that within the critical angle of incidence can go get emitted out and propagate to the other side. And so in the far field, the limit is the blackbody radiation. And when the incidence angle is larger than the critical angle of incidence, there's an evanescent wave. It's just an evanescent wave decay rapidly over the order of wavelengths. So normally, they do not propagate out, and they don't carry energy. So again, when the space is far, the limit is a blackbody. However, when we bring the other surface close by before the field decay to negligible level, then radiation can tunnel from one side to the other. This is the same. A lot of people here work on photonics, and the same principle. It's just here the source is the thermal source. So you have the tunneling, and in the limit, when the two surfaces gets really close, they contact each other, the blackbody radiation inside a material is proportional to refractive index square. So that's an n square effect. And if we take silicon as an example, n square is about 10, dielectric constant. So you say, okay, we probably can increase the radiation by a factor of 10. But that's not the limit. And we can look at another situation. This is a surface wave. And again, I'm pretty sure a lot of people are familiar with surface plasmons. And there's a sister phenomena to a surface plasmon, that's a surface phonon polariton, which is a polar material where you have positive ion, negative ion, and the resonance of electromagnetic field with the ionic vibration give you the phonon polaritons. And this phonon polariton could have a surface wave that existing that decays on both sides of the interface, same as surface plasma. And in this case, the dispersion is between the transverse and longitudinal optical phonons, and it can have high energy states. So here is a calculation of the energy density of states. Here is blackbody radiation, black bodies in free space. And because of the resonance, you can see here is the energy states many order of magnitude higher than the free space density of states. And so again, when we bring another surface close by, the tunneling will happen. And in this case, because of the high density of states, you can have very large increase in the thermal radiation from one surface to the other. So how you do this calculation, it turns out the theory is there. This was established in 1970s, starting with it's basically using fluctuating electrodynamics. And we think about a source here, you use Green's function, and calculate if I have a fluctuating current, what's the electromagnetic field generated. And this fluctuating current is related to the imaginary part of the dielectric constant and related to the Bose-Einstein distribution. So with that, you connect with local temperature. And so basically, it's electromagnetic wave calculation. There was an alternative explanation based on John Pendry, and basically say this is a quantum transport, and what's the maximum energy per channel. So it has a limit on the maximum heat transfer. But say if we do that, and it turns out that any polar material could have this surface phonon polariton. So even glass, and this is the dielectric constant of glass, and here is about 8 micron, and you can see the dielectric constant is negative, and same as the surface plasma. So when dielectric constant is negative, you have the surface waves. And then say when we bring two surfaces close by, one is hot, the other is cold, and in this resonance range, you have much higher energy flux from the hot to the cold side. And if you integrate over all the energy, you get a heat flux from hot to cold side. You can say is many order of magnitude higher than the free space blackbody radiation. And so this is it's established. You can do the calculation, and the question is, can you do the experiment to prove it? And turns out that this near field enhancement of radiation heat transfer. Actually, the experimental work started with my PhD advisor Chen Tian, and he did some experiment in the 1970s, but in very low temperature. And there's a small trend of increase in heat transfer. And in also around the same time, Phillips Research Lab has some work between metal surfaces. So if you do metal, it's actually hard to go beyond the blackbody radiation. If you go convert those, it doesn't go through the beyond the blackbody radiation. So we work on this experimental side, consider different possibilities to do the experiment. And one can start with the simplest is the parallel plates, because the theory is well established for parallel plates, and or a sphere and the plate. The parallel plate turns out the difficulty is maintaining two surfaces parallel and down to nanometer regime. And if you have a sphere, experimentally you can see it's always aligned, and that's an easier experiment to do. and also the calculation. So we consider all this. We started with two parallel plates. And how we do it is we use this polymer spheres as a spacer put into the hot and between the hot and cold. And because of the polymer sphere and a very small radius, and you do conduction heat transfer because of the K is what's the heat leakage through the spheres. And with that, we say the our calculation shows that the conduction heat transfer is less than 1%. So we're doing two basically quartz plate, and one side heat up, the other side we measure the heat flux, and we had some experiment reported. So here is blackbody radiation, and here is when the two surface is of the order of micron, and here are in the far field, and you can see with that we can go beyond the blackbody radiation. But when we do theory, we see nominally this sphere is 1 micron, and the experiment is here, 1 micron is here. It turns out the sort of experiment is falling in between 1 micron, 1.5 micron. And the reason was this sphere is not a uniform diameter, and when we do spacing control, it's the larger diameter that determines the spacing. But when we try to push this to smaller spacing, didn't work. If you think about the two surface maintain of the order of ½ inch, you want to maintain parallel less than micron or ½ micron, that's very difficult. Any dirt will create trouble for us. So then we went back and then we say, okay, can we measure a sphere and the flat plate? And the question is, how large is the heat flow? Because we need to have some order of magnitude. So the first thing we did some calculation. It's easier to calculate two spheres. Later on, a lot of people jump on calculating this sphere and plate, which is really difficult from an electromagnetic wave perspective because of the geometric asperity there. But we first did the two spheres, and our calculation shows this is the sensitivity range we need. We need about 10 to the minus 8 watt Kelvin. So basically, we need to measure heat flow in the nanowatt regime. And so the technique we turn on to, again, probably some people is familiar. I think there are a lot of work in Santa Barbara before on when Arun was here, Arun Majumdar was here, doing the bilayer cantilever as a thermal sensor. All right, and it turns out that you can use the AFM cantilever when it has two different layers. It's a very sensitive thermometer, and because of the thermal expansion mismatch between the metal and the dielectric cantilever, and very small temperature change will create the bending of the cantilever. And at the time we measure our cantilever, it could have really tens of picowatt sensitivity and millikelvin temperature range sensitivity. So using that, we say, okay, let's glue a sphere onto the cantilever, and we can use this as the heat flux meter and measure the heat flow between the cantilever, so a sphere and flat plate. So the first thing we did is the same as just a normal AFM cantilever. We glue a sphere, and but say we're saying as we move closer, the cantilever will bend, and that's the what we're trying to do. But it turns out if you use the AFM, it won't work, because once the distance goes to 50 nanometer or 100 nanometer, the van der Waals force will just slap the cantilever onto the substrate. So we had to turn this, reset it up, and turn this into 90 degree, and that way we can avoid the force effect. And so this is the typical experimental configuration we use. We glue a glass sphere onto a cantilever and do the basically force, say the bending measurement. So it's very similar to AFM, And in this case, the laser serves two purposes. One, it heats up the cantilever. When you put this in vacuum, just an AFM cantilever heat up about 20 degrees. And second, it measure the bending. So this is a heated cantilever. When you approach the surface, you will have the say the near field will create the bending of the cantilever. So this is if you do the analysis, because the surrounding is at the ambient condition, and when we do the analysis, we found that actually the initial bending is the far field, and the initial bending cannot be measured. So we really just measure the near field heat transfer, because the far field is a combination of conduction and radiation. So those were some of the data here. When we go approach the surface, you see the conductance increase, and that's the near field effect. And when we the question is how we can compare with theory, because now we have a sphere geometry. Like I said, this is actually really hard to compute. The sphere is about 100 micron in diameter, and this spacing is about 30, 50 nanometer. So you got a very wide range of wavelengths, and it's difficult calculation. So we use the proximity theorem, which is widely used in van der Waals force theory, Lifshitz force theory, and then approximate this as a parallel plate and do integration of that. And so if you use this proximity theory, this is the parallel plate result. This is the effective area, and converting the conductance back into the parallel plate result, you can say the radiation is many order of magnitude higher than the blackbody far field radiation. And so that's the glass surface. And then we went on to measure metal. So this is a metal surface, and metal is not as good as the glass in this case. And but you can say that our data pretty much stopped at 30 nanometer or so. And so the question is, we're asking is, what if we get closer, right? And here we still use the language of photon, near field radiation. But you can think about when two surfaces get really close, right? And what's amazing is when we have two surfaces in contact, we do heat conduction. We do phonon transport. And in this case, the contact resistance or thermal contact conductance at the interface is 10 to the 8th. And what we have done in our experiment is going down the separation to about 30 nanometer. The conductance now we have achieved is about 10 to the 4th. So between contact and 30 nanometer, there's another 4 order magnitude change in the transport mechanism. And it's interesting to ask, in this regime, what's the right language? What's the right picture? Because in the contact regime, we use the phonon transport picture. And in the near field, we still use the photon transport picture, right? How we describe it from basic theory perspective. And so one side we're trying to push the experiment to contact regime, and we're designing different cantilevers, doing the experiments. And we have not published. This is actually after 3 or 4 years of work. We have not published it because the surface roughness has plagued us. It makes the data interpretation much more complex. So we're trying to make smooth surfaces. At the same time, we're also developing a theoretical approach. I already mentioned the STEGs approach is from electromagnetic field point of view. Fluctuation dissipation theorem considers the thermal source is a current source and generate electromagnetic wave propagate to the other side. And that's the calculation we have used before. And this is based on the macroscopic Maxwell equation, dielectric constant. But see, when we go to this contact, And what we have to do is actually go into microscopic Maxwell equation. We do not use dielectric constant. We use basically the atomic vibration, generate the electromagnetic field, and also include both the near field, and calculate the F equals ma. So in this case, we want to calculate atomic motion doing the lattice dynamics by including the electromagnetic wave interactions. So that's the approach we're taking from the theoretical side, and we have some preliminary results. And let me just show you this result. Here is the case of perfect contact between two sodium chloride crystals. And you can see in perfect contact, the transmission from one side, what we calculate is transmission from this side to the other side, and is dominated by mostly acoustic waves. And then once we go to 0.5 nanometer and 1.5 nanometer, you can see transmission becomes much smaller, and gradually the optical phonon becomes comparable. This is the optical phonon is the one I talked before, the phonon polariton contribution to the transport. So this is a really very interesting regime to understand the conduction, understand the radiation, understand the convergence. And we've been working on this for quite a few years, haven't published much. It's a very complicated issue here and of interest. So, yes. This is not a normalized. So here is actually density of states. So it's not normalized to the density of states. It's per channel. So if you have, for example, you look at these three, there are three polarizations. One longitudinal wave, two transverse wave. That's why you can see the maximum there is 3. So we also have normalized data. You normalize to density of states, you'll get the absolute transmittance. Yeah. So that's this side is more on the fundamental, and now I'm going to turn a little bit and talk about two more applied topics. And one is because here what we're interested is manipulate photons, and so I will talk. This is a project we've been working on for a few years, and it's actually just started with a graduate student. He really wants to work on. He was doing near field. He said, "I want to work on more the photovoltaic side." So we started exploring different light trapping, electromagnetic propagation problems, and looking into plasmonic and looking into nanowires. And eventually, we started really making crystalline silicon thin film solar cells. So let me just say, framing this motivation for this is, if we look at the photovoltaic, the goals here are the cost. This, I think, this is depends on who you ask, and there are some artificial pricing problems in the market because of oversupply. So in China, you can buy the photovoltaic module at 60, 70 cents per watt. And I want to say that when the U.S. Sunshot project started about 5 years ago, this is Secretary Steve Chu launched the Sunshot initiative. At that time, the module cost was about $3.50 per watt. And the goal was by 2020, the module cost dropped to 50 cents per watt deployed. And I thought that at the time was really very ambitious, but it turns out that the industry moved much faster. And but overall, you see here is the cost, and in terms of module, you have a wafer, you have cell fabrication, and then packaging into the module. And by the goal is getting to about $0.50 per watt, and the other $0.50 is for the balance of system, the rest of installation, framing, and inverters. So most of the current silicon module is based on wafer and with a thickness about 300 microns. And the reason for one of the main reason for this thick wafer is the absorption. Of course, silicon is an indirect gap, so absorption is not good. So you need a much thicker wafer to do it. So a lot of people doing light trapping, trying to use much thinner material to get a similar absorption and get to a higher efficiency, reasonable efficiency. So we, like I said, when we start looking into this, we look into nanowires and plasmons. But at the end, after we consider all the charge transfer and look into different structures, look at how much surface area we increase, and we look at these are the simulations. Basically, those simulations says if I compare to wafer with the anti-reflection coating, this is a wafer-based, with versus with structure surface, we can get a 10 micron. Within 10 micron, we can get a similar efficiency as a thick wafer-based silicon cells. So with that as a motivation, we say, okay, among all this, what would be the easiest to make and to fabricate? And this is the silicon, say, thin film with the inverted pyramid, because we know that you can etch it and easily with chemical etch. And also, this has a much less surface area increase, and that is beneficial when we look into the efficiency. So that's an optical design, and then we did some electrical simulation. This is a device simulation. It's drift diffusion equation, and with contacts and absorption, light absorption. In fact, stitching this together actually took some time. Consider all the effect, surface recombination, bulk recombination, and how to do the different doping, electrode profile. And so basically our goal with those simulations is say if we might be able to achieve over 15%, 15-20% range with a less than 10 micron silicon cell. So with that, we have a very brave graduate student and went to the clean room and using SOI wafer. So it's a lot of fabrication steps. And here I'm not going to go to detail. And so we made a cell, and some examples of this. This is the light trapping structure. It's about you can say it's about the 500 to 700 nanometer range, periodic. And we measure the absorptance, and here is the optical experiment only. So this is the you can see the measurement compare very well with the theoretical calculation, and it shows that the absorption of this silicon film could be actually very good. So here is the absorption of a 10 micron silicon cell and versus a 375 planar structure, and the absorption again could be comparable, better. And the cell so far we achieved is about 14% efficiency. So this is if a graduate student, this is sometimes it could be very, the competition is actually very strong, and we saw that we want to get the 15% to publish, and then say this last month there was a paper in Nature Communication. The title is 13.7% efficiency. So we're here, and the Stanford group have the same data. Is also about the same efficiency. We're trying to get over 15% efficiency with this. So that's where we are. And my last topic is going to, again, so I said a little bit disparate topic today, but it's going to be completely different. And this is a steam generation. So solar, come back to solar thermal, and how I can use the sun to generate steam. And if we look at the current way of solar thermal, this is a solar hot water system. And it's typically a vacuum tube, and with metal, copper coated with selective surface. When I say selective surface, is a surface that absorbs solar radiation but minimizes thermal re-emission. And I want to say that because in our center we also work on 3D photonic crystal, 2D photonic crystal, and my collaborators, this is Marvin Solisik, and I always remind him, because I went to China and visited those companies before. Those kind of coating is a vacuum coating, multi-layer vacuum coating, and the chamber is as long as a football field. And that's how they make it over 140 million square meters. It's very industrialized. And so there are different geometries, but this generates only solar hot water. So this is for household hot water. And of course, to get to higher temperature, you need a concentrate. So here is a solar thermal power plant, parabolic trough. And again, it's a vacuum, right? Inside you can see it's black. Outside is glass. It's an evacuated tube, and the solar radiation is focused into the center. And this focus, the concentration is typically around 50 times. So 30 to 70 times in a 12 system. So that's the state of the art. And last year there was an interesting study by Rice Group. This is Naomi Hollis. And what they did is they put the nanoparticles into water, and then they use a concentrated sunlight, and they demonstrated that they can generate steam when the surrounding is ice. So this is a localized heating, and it drew a lot of attention. Their first paper was published in ACS Nano, and it was the most downloaded paper for many months. So a lot of attention. And subsequently, they published some of the data in terms of efficiency and more concrete data. And they say it's about 24% efficiency under 1,000 sun concentration. And very interesting. The mechanism, I think even nowadays, they're not very clear mechanism how the localized steam is generated. And but this got us thinking. So can we really generate steam differently from what been using in the current solar thermal systems? So we came up with the idea of local. So basically, what the Naomi Hollis was doing is using nanoparticle to absorb solar radiation, right? So generate local heat source. And so the question is, what's a good way to generate local heat source? And we used this two-layer structure. So here is insulating, thermally insulating layer. Here is absorbing layer, and here is water. And so this is in fact, it's pretty simple. It's a graphite. Graphite flakes on graphite form. And so water is hydrophilic. So water is actually sucked into the top surface layer. And then with that, we can generate, say this heat is absorbed in this region rather than just normally when we want to do evaporation, if it's shine solar, of course, light is absorbed through the whole volume. And so it's quite effective. And I'm going to show you some data, but you can say just from the vapor, that's pretty effective. So this is a double layer structure, and here is the optical concentration. This is one sun, and we measure the rate of evaporation. From that, we know how much energy is going into steam or vapor, and then we also know how much solar radiation comes in, so we can calculate the efficiency. And here is the efficiency. Oops. So you can say that the efficiency we achieve is over 90%, and under 10 sun condition. And what's interesting is the liquid is cold. Here's the water, and here's the vapor, steam. We did this under 1 atmosphere pressure, so the steam is only over 100 degrees. But say you could generate create steam quite effectively using this approach. And if we compare under 1 sun condition, this is the different, this is water temperature, right? If you just don't have any absorber there, water is here. And when you use double layer structure, in fact, because most of solar radiation is absorbed in the top layer, so water is cold. And under different concentration, the vapor temperature increases. And in terms of the efficiency, we compare different. So this is just a shine light directly on water, shine light water with graphite, or with this double layer structure. And you can see that the efficiency, this is a 10 sun condition, 1 sun, 2 sun, and 10 sun. And we get a pretty effective water evaporation. So we're actually working a lot. This is beyond we're doing solid state. Now we're actually getting also back into my mechanical engineering route, looking into those phase change materials. So with that, I want to wrap it up, and want to I talked about the more on the fundamental side, near field radiation, thermal radiation, and this actually bring very interesting question on the convergence between conduction and radiation. And we know in terms of heat transfer, there are 3 modes: conduction, radiation, and convection, right? Now, this problem actually say, okay, in this regime, conduction and radiation becomes sort of described under one equation. And I described some of the ongoing work in the silicon solar cells and the steam generation. And on the steam generation, we're also, we think we have some data we can build pure vacuum systems. So using this type of approach. So with that, I want to thank the students and who really do the work. And I'll stop here. I'll be happy to answer questions.
Questions? So a general question on your heat transfer between, you showed silica having higher heat transfer than between 2 gold spheres.
Right.
Is that in general true because of the emissivity of gold or something, or why is that?
Well, so in this case, because this is first the metal emissivity is small, right? And also one could argue, why don't you work on the surface plasma regime? But say surface plasma of the metal is typically very short wavelengths. So the glass is the wavelength is about 10 micron, 8 micron regime. So actually just right for the thermal emission. So that's generally most of the time when we work on those polar materials, even gallium nitride, they should all have similar phenomena. It's just we haven't done this experiment.
Yeah. So in terms of using this for heat power generation, I guess I was assuming you have this broadband absorber, and then you transfer across to this narrow energy band.
Right.
And then you have it has to be a band-to-band detector at the other end.
Right. so this is where I looked into a lot of different material. What would be the material that has the right, because of the 8 micron is just too long, and some of those material, for example, boron nitride is about 5 micron, and the question is whether there are materials like 4 micron range or 3 micron that probably will go to some hydrides because of hydrogen bonds. Say hydrogen with a smaller atom. Basically, you want atomic vibration, high frequency atomic vibration, to gear towards the band gap. I have not found the ideal material for that. Yeah.
Other questions? Yeah, Bridge.
I was wondering if you have looked at the possibility of other refrigerants rather than just water and getting.
Oh, excellent question. Whether we have not looked into right now for our experiment. We're pretty much working on water, but the same principle, right? You should be able to. In fact, you probably also think about in this. There one could think about the organic, say Rankine cycle, yeah, because yeah, you could potentially get into. My dream is here is can I just do a few hundred degrees steam without any optical concentration? Because then I don't need a tracker. That might need to cheap solar thermal to electrical energy conversion route.
Yes.
Is the evaporation flux greater for a gold color?
Actually, no. So we've been doing. We think we understand what's going on in Naomi Hala's experiment. It turns out that because she started with the idea of surface plasma, but you go to read her paper, she will say that all the calculation doesn't explain the experiment because it just if you have an isolated gold particle, even with the surface plasma enhancement of absorption, your temperature rise is still less than 1 degree. Locally, the metal particle temperature rise is still less than 1 degree. So they couldn't quite explain the experiment. But if you go to look at their experiment, they also have carbon black, which doesn't have surface plasma, and it has a similar effect. So we have some experiments in their similar systems, and we think this is really related to the cluster of the material formation, and that form the special structure that's conductive to in terms of the vapor formation.
Any other questions? All right, let's thank Gang again. Thank you.
Thank you. Thanks a lot.
So, what about just using